Okay, welcome back. So last time we were talking about the electric potential. We're going to continue with that today. We're going to take a look at it and figure out a way that we might draw it the way that we drew the electric field lines to try and get a better understanding of what's going on. Then we're going to go back to something we talked about before, capacitors, and see what happens when material is introduced inside a capacitor and how that affects the capacitance and things like that. Okay, first let's go back to the gravitational analogy. We know that if we have some object, some mass or something like that, we can define a gravitational potential energy that depends on the mass of the object and where it is, in other words, its height relative to some arbitrary zero height, or say the zero of our coordinate system. So let's imagine we have some ground level or whatever where we want to define our zero height, and we've got some object with a mass m. We can then define the potential energy of that object, which, if you'll remember from last semester, 1111, is mgh. We might, if we want, define a gravitational potential kind of analogous to the electric potential, where we define this quantity as the potential energy per mass. So we might define this as the potential energy per mass of our object. We might think of this like a test mass. As we had a test charge that we used to define the electric field and the electric potential, we might think of this as a test mass that we'll use to define the gravitational potential. So what's the potential energy divided by the mass? Well, that would be mgh divided by the mass, or just gh. So that's a quantity that is independent of the mass that we're using here and only depends on the height that we're talking about, h, above the ground level, only depends on h, but then also the gravitational acceleration, g, basically the strength of the gravitational field. If we were far away from the Earth's surface, it would be a different value and our form would be different. But remember, we derived this for being close to the Earth's surface, say within 5 kilometers or so. It's a relatively good approximation. So we can define then this gravitational potential, not potential energy, but gravitational potential, which only depends on the strength of the gravitational field and our position, the height above our ground level. And there we go. Okay, so how might we apply this to a physical example, staying with this analogy? Well, let's imagine that we had, say, a hillside or something like that, or a mountain, a small mountain, maybe something like, well, nearby here, something like Stone Mountain. If you're not familiar with Stone Mountain, it is close to Atlanta here. It's basically got one side that is relatively not very steep, and then the front side is much steeper like that. So imagine that we've got some hillside that is very steep on one side, not so steep on the other. And let's think about the lines or the areas on this mountain that have an equal potential to each other, that is. Well, one way we might imagine this is, let's take this mountain and stick it in a gigantic bathtub sort of thing, and let's pour in 10 meters of water. So we pour in 10 meters of water, the water level comes up and surrounds this hillside. This is kind of an odd way of looking at it, but here's our 10 meters of water. 10 meters of water, and then there's this shoreline that goes around the mountain, all at a height of 10 meters above, say, our zero level, whatever that is. So let's imagine we draw this shoreline around the hillside. Then we add in more water, another 10 meters. So we pour in 10 more meters of water. We get a new shoreline higher up on the mountain, now 20 meters above ground level. 20 meters above ground level around the exterior of the mountain. Then we put in another 10 meters of water, we get a new shoreline, another 10 meters of water, a new shoreline, and then finally the whole thing is submerged. Now let's imagine we look down from above and we look at these shorelines all at different heights, and let's imagine we graph them or make a diagram of them. We might get something like this. So here's one shoreline at 10 meters, and then this one at 20 meters. And the next one at, say, 30 meters, and another one at 40 meters, or something like that. Okay? And you can imagine, here we go, these lines are like this, here. Now, this is exactly what you get if you have a topographical map. If you've ever seen a topo map of a hillside or mountains or something like that, if you're going hiking or climbing or something like that, you might use one of these to see what the terrain looks like. Now, what can we get from this image here? Well, we notice that over on this side, these lines are close together, while on this side, the lines are much further apart. Now, why is that? Well, over here, these lines are close together because the hillside is very steep. So these lines are close together. While over here, the side of the hill is not so steep, and so these lines are further apart. So the fact that the lines here are close together tells us that we have a very steep part of the hillside, while the lines over here are further apart tells us it's a much less steep part of the hillside. Okay? Well, we might think of that as this is a region where the gravitational force pulling us down is down the hillside is very, very strong, while over here the gravitational force pulling us down the hillside, because it's not quite so steep, is going to not be as strong. Much stronger force here, not quite as strong force over there. Okay? Well, these ideas are very, very similar to the sorts of things that we'll see for the electric potential. Now, one thing I want us to think about is, let's imagine that we are, say, standing here on this shoreline. Now, this line, if we think about it, would be a line of constant potential energy for us. If we were to stay on that shoreline, we would not change our potential energy. In other words, we would not change our potential, our gravitational potential. So this line is a line of equal potential. In other words, it is what we call an equipotential line. A line of equal potential, in other words, an equipotential line. This line, every point on that line has the same value for the potential. In other words, the same height, the same value of GH. This line does not have the same potential as this line. So when we say equipotential lines, we don't mean that one line has the same potential as another line. What we mean is, excuse me, that every point on the same line has the same potential as every other point on that line. So these lines are what we call equipotential lines. Gravitationally, we can think of them as lines of equal height. Equal height, equipotential. Okay? Now, one thing I want us to keep in mind is if we were to walk along an equipotential line, so imagine we're standing here and we walk along a line, how much work would we have to do in order to do that? How much work would it take for us to walk along an equipotential line? Well, if we think about it, how much are we changing our potential energy? Well, we aren't. If we stay on an equipotential line, we are not changing the potential energy. If we don't change our potential energy, how much work do? We do zero work. So the amount of work required to walk along a line of equipotential is zero. Well, how did we define work? Back in last semester in Physics 1111, work was defined as the force times the displacement times the cosine of the angle between them. Theta being the angle between the force and the displacement. Well, if this is 0, what does that tell us? Well, either F delta R or cos theta is 0. Well, F is not 0 because we know we've got some gravitational force. So there's some force. If we move along the equipotential line, we know we've got some displacement, delta R. So F and delta R cannot be 0. So what has to be 0? Obviously, cos theta has to be 0. Well, if cos theta is 0, what does that mean? It means that theta must be 90 degrees. Which means what? That the force and the displacement have to be 90 degrees to each other. In other words, they have to be perpendicular. If the displacement is along the equipotential line, that is telling us the force must be perpendicular to the equipotential line. Now we know in this case gravity is not pushing us up the incline, so we know gravity must be pushing us perpendicular to the equipotential line. This is a very, very general and a very, very important result that we need to keep in mind. The force acting on us. Now what force is this? It's the gravitational force in this case. It's the force that is creating the potential energy. The force that is creating the potential. The force that is acting on us is perpendicular to the equipotential lines. So this is a very, very important result. The force is perpendicular. Whoops. The force that is creating the potential is perpendicular to the equipotential lines. Okay? All right, so there's the gravitational analogy. Let's go back to what we know about the electric force. Let's start off with the simplest case that we have, point charge. So let's imagine we have a positive charge, to start with, a positive charge plus Q. What does the electric field look like for a positive charge? Well, we know electric field lines always point away from positive charges. So you might remember the electric field diagram looked something like this. The electric field lines always symmetrically pointing away from the positive charge. So those are the electric field lines. Now let's see if we can figure out what the equipotential lines look like. Well, let's remember our form for the potential for a point charge was equal to V equals KQ over R. So for a given charge, Q is a constant, K we know, Coulomb's constant, that's a constant. What is the only thing that we can vary in this equation to change the potential? Well, it's R, the distance from the potential. Now, what values of R will give us the same value of V? Well, whatever value of R, whatever points that have the same value of R will give us the same values of V. Remember, R is the distance from the charge Q, so this is telling us that any point that has the same distance from Q will have the same potential. Well, what are those points that are all the same distance from Q? Well, if you think about it, they're points on a circle. Or, in 3 dimensions, they would be points on a sphere. So a sphere centered on Q. Well, what does that mean? That means that any point on this circle, or on this sphere, will have the same value of R, the same distance from Q, and therefore will have the same potential. So the equipotential lines, or in 3 dimensions, the equipotential surfaces, will be concentric spheres centered on Q. So, spheres, circles. So the equipotential lines, or equipotential surfaces, are all concentric spheres centered on Q. And what do we notice? Well, we know that radial lines and spheres are always going to be perpendicular to each other. So we know that these are always at 90 degrees. And that is exactly what we just came up with our gravitational analogy. So what we see again is that the equipotential lines, the equipotential surfaces, are always going to be perpendicular to the lines of force. And again, remember, the lines of force are the same direction as the electric field vector lines. Either same direction if you put in a positive test charge, opposite direction with a negative test charge. But the bottom line is that the equipotential lines are always perpendicular to the electric field lines. Okay, so we kind of verified that with this example. Let's see how we might use this to come up with what the equipotential lines would look like for, say, a different sort of diagram.